Hey everybody, it's Beard, and in today's shader tutorial we are going to cover screen space reflections, which we see here with our cloud style 2, which is the volumetric ones. Let's switch it over to our default settings. We're going to do this the way we did the other ones, which the last tutorial, which is more of a here's the finished code and let's walk through it together and then play with little bits of it to see why they're there, instead of doing it live. Because it's just it's a chunk of code. So we're going to do the water, and we're also going to hard code iron blocks so that they will have a reflection as well. But we'll also read PBR textures to even do things like having rough reflections if we use a resource pack that has PBR data. Like here's with the Patrick's pack. The reflections should have some roughness to them. We will go over all of this in detail as we go through it, but first we're going to go through the concepts. We're going to go over the concepts first, and then from there we will get into the code. Because I want to make sure you understand how this works so you can do what you want, because there's a few different ways you could actually go about this and ways that you can optimize it. The first thing we need to think about is that this is our screen, and that is that cat is fine. He's just doing his parade with his toy where he drags it around and does the song of his people. But if this is our camera's view and we've got, let's say, ground over here and it goes all the way into the background, and then we've got a mountain, and let's say we've got like a box here, that's going to be our scene. This is our screen, so all of the pixels have a position. Let's look at this from kind of like a bit of a different view. Let's make a 3D view of it, and we're going to kind of do these two spaces and how we do this. You can pretty much do most of this just here, but for accuracy we're going to do it in this kind of cube space too, and then there's ways to optimize it, do more of it here. But in this view, let's say our mountain is way back here. Let's say it's this far. Like here's on the ground. Here's where our cube is, our box, and there's all the ground. And here's our camera, just over here. Like let's say right here in the middle of this plane. Now something we're gonna do here is perspective. So I'm gonna draw the camera's perspective. The camera sees things like if you do drawing, you know, like if you did perspective, you draw lines like this. And the reason those lines look like that, even though they're just kind of straight on the floor, is because the camera has a perspective where it's viewing kind of like what's in the corners more, you know? Like, so things to look bigger as they're closer. So here's an above view, and here's the camera, and here's the mountain, and here's like the box. If the grid of the world is like this, when you put it in that perspective, it gets kind of put like that. We're going to put things back and forth between a space like a screen that has perspective and a space that doesn't, to figure out where things are on the screen. And to do the reflections, the basic concept is, if this is the ground, like here, and here's the mountain, and here's our camera, if this ground is shiny, like this would be a reflection of this, this would be a reflection of the mountain. Things kind of line up because the light bounces off at the angle of what it's hitting. Like whatever angle it comes in at is the same angle it's going to come off at. So if you hit here, you're going to see this. If a view angle is to here, then it's going to come off more shallow like this, and you see it like that. If you look straight down on something, you're going to see straight up and see what's behind you. And that kind of thing is why mirrors end up giving you the kind of upside down or sideways, backwards reflection, is because of the way the angle, you know, just comes straight back at that same angle. So it ends up kind of flipping stuff. So what we're going to do for screen space reflections is we're going to look at the depth texture, because it tells us how close things are to us. In the depth texture, anything that is close to us is either like, it's a 0 to 1 range, but you could view it as like black. Like let's say like anything super far away, if we wanted to think of that as black, this guy would be black because it's infinitely far away. and then things that are closer, like halfway, would be gray, and things that are closest would be white. It's probably the opposite, but we'll look at that and visualize it, since that's the data we're playing with. And what we're going to do is, for each pixel on the screen, we're going to translate it through those world translation sheets we've got, that chart, and figure out where it actually is in the world in an unprojected space that's actually cubed and doesn't have this warped space. Because this is just like a yeah, I mean, it's our screen, but it's not space. So we're going to figure out where each spot is in space. So let's say we wanted to figure out right here next to this. We're going to figure out that that's here, and then we're going to look at where that is compared to the camera, so we can trace a ray to it, bounce off at the angle of based off of that, and then bounce off and see where it hits. Some of the things that we could do differently from what we're going to do today, I'll go over real quick, is we're going to be going back and forth to do this because it's easier to explain and it's conceptually easier. But there's also different ways that we can optimize things differently. We're going to trace based on distance. So we're going to say that if this thing is halfway between here and as far as we see, then we know how far the furthest the ray needs to trace is however much space is left for our render distance. So we're going to use that. Alternatively, you could take this, and knowing which direction we're going in, like if we're tracing off at an angle here maybe, you could then stretch that reflection angle all the way to the edge of the screen and then you could just like interpolate here instead of going back and forth with doing the projection. And that might be faster, but we're not going to do that. I just want to drop that as like a possibility for you. But there's possibly an optimization there. I'm not sure if it gets distorted. It might not on straight reflections like this, but if you were to do like a lot of rough reflections, it would probably get a little distorted. But we're going to go back and forth. That's a possible optimization. That's the concepts, and let's get into it. Okay, so if you get in your Minecraft, first thing I'm going to do is I'm going to cut down my frame rate to save some on that, and go into our shader pack settings. Since we're starting with a completed shader, we're just going to reset it to the default settings. The new stuff we're adding is in our reflections menu here, and we're going to go through some of this as we go through the code. Today's episode is brought to you by my Patreon and YouTube supporters, and by Sasha the cat, who you may hear purring, and she may jostle the microphone. She is right in my face blocking the screen. Let's look at some of this in the shader real quick. We have a thing to turn our reflections on and off. That's pretty self-explanatory. We can control our fresnel. So here you can see stuff is shiny at a distance. Maybe we didn't actually implement that. So we'll look at that as we look at the code. I may have not done that well. So let's reset that. A reflection threshold is an optimization where we stop things from being reflective if they're not. We always want water reflective in the way we're optimizing this, but to save frames on lower end PCs, we have an option where things that aren't very shiny will not do reflections, because instead of running reflections on literally everything. Our Fresnel exponent controls our Fresnel. If we set it to 1, then you can see the water is reflective starting from very close to us. Like you can't see underwater at all. And that option is there for debugging purposes, but also I guess artistic if you want. We're defaulting on 3, which you can see the kind of fade this gives as things are further away. The water is more reflective. A more realistic standard for most materials, in my opinion, is 6. But that doesn't really give you much reflection on water. So like I like taking artistic license with things. So we've got that as a default of 3. Our main performance things is going to be our SSR steps, our screen space reflection steps, and our refinement steps. the initial steps is how many times when we're tracing. Like if for this spot of water, it's reflecting the top of that tree. So this screen space reflection steps is how many times it's checking if it hits something. And then the refinement steps, which we'll go over, is where it's kind of fine-tuning where that hit is. So we'll get into that in a bit. And high quality normals, this we will also show what that's about. So let's reset. Let's look at our code. Okay, so the first thing in our code is we're going to go to our block.properties, and we are going to define some IPBR metals and an IPBR water to deal with what we're doing today. So we're going to say that water is number 10,006. I'm going to say that iron and redstone and gold are 10,007. So those will be our metals, and this will be our water. Once we've got that, that's all we need to do here. So we can close our block.properties. In our settings, we have some new settings we're using. So for tutorial 13, we're going to have our reflection threshold, which again is a performance helper, our Fresnel exponent, so that we can adjust that artistically, our screen space reflection steps, our refinement steps, whether or not we're running reflections, and whether or not we have high quality normals. And we may have more debug views. I'm not sure if I put those in. Because I'm re-recording this, I lost the recording. So that's everything in our settings. In our shaders.properties, we're doing a little bit of new stuff. We're putting certain things up here in our sliders, just so they've got sliders, like our Fresnel adjuster and all that. We are giving a new screen called reflections. We're putting it on our main screen in the square brackets. And in the screen itself, we're putting all the things we're using here for our reflections. And it looks like we've got our PBR screen, in which we also control our Fresnel. And what was this? Let's look at our settings. I don't remember what this is. We have a PBR toggle. So we'll see if that does anything too. That might do something in this code today. Or that might have just been for our PBR tutorial. That's what that was for. So also in our shader.properties file, we also down here at the bottom, when reflections is off, which in this case we're using 0 and 1, because I like to do it that way, then maybe make incrementally different, more expensive versions of things. If it's off, we're saying program.composite4.enabled equals false, which means we are not running composite 4, which is where our reflections will be if the reflections are off, so that we say performance. That's everything in there. Now we're going to defer the reflections. We're not running them immediately. We're running them after the other stuff renders in the composite. So in our main, we need to pass some data forward where we have our render targets, or this may be whatever the old option was in the other shader we had before. We're saying render targets. These are separated by commas. Instead of just writing to 0, which is our main buffer, we're also writing to 2 and to 3. So our flag.0 is this, flag.1 is the second thing we listed, and then flag.2 here would be this third thing we list, because things start with 0 instead of 1 on computers usually. And if we're using the option of high quality normals, we're going to say that, or this is how we declare the format for buffers. Instead of being a red, green, blue alpha with 8 bits for each, these are going to have 16 bits each if we're using high quality normals. And then we're going to write our data and our color. In our main one, we save our main rendering color. And frag.1, which is buffer 2, we save the normals of our texture. And what we do is we do it times 5 plus 5 to do that trick we've done before, where if we have a number that's both negative and positive with 0 in the middle, and we want to save it in a 0 to 1 range, which the 8-bit buffer is, but the 16-bit buffer is not, we're going to squish it down so that it works with either buffer. So we take that -1 to 1, we half it and add half, and that squeezes it in that 0 to 1 range. And then we're just not using that last channel. And then in flag.2, which writes to texture buffer 3 or color text 3, we're saving our smoothness. This is the PBR data that deals with reflections. Our reflective strength, which is a combination of our F0 and Fresnel. This here we're seeing if it's related to 10,006, which is our water. So we're seeing if this is water, and putting either a 1 or a 0. And then the F0 we're saving. We're saving that subbit from this with the Fresnel included as a bit of a performance trick where we can just check if something is water or is reflective enough to need a reflection instead of just running reflections and everything. So this is the data we are deferring. And now we're doing deferred rendering because we're doing some of the rendering later, not just in the G buffers. So that's everything in our main. And then composite 4. This is where we're doing reflections. If you're starting from scratch, this would just be like the version, whatever, include our settings. We're adding the uniforms, data from Minecraft. We're sampling different textures. This is our default one we're already using. Color text 2 and 3. These are our normals PBR data that we're passing forward. Here's our depth texture that we're sampling. And here is some distance data we're getting from Minecraft for linearizing our depth. And here's our projection stuff. Data we're getting from the fragment trader is where the pixel is on screen. And here we're enabling mipmaps for color text 0, which we will use for our rough reflections. This is a function to linearize our depth, which we then call through our getDepthAt function, which gets the depth at a specific pixel. And we're abstracting this because we want to be able to work with this in horizons later. And when we do that, there's 2 different depth textures you sample from instead of just one. Here's our thing we use for translating back and forth, like I showed on those pictures, between where the pixel is on screen and where it is without perspective in more of a 3D space. And then here's our main function, which the goal at the end is that we are just writing to draw buffer or render target 0, and what we're writing is our final color. So with that said, let's look at what that thing in main did real quick and why it exists. That high quality normals option. I'm going to get here and just park myself here, and you can see that if I walk, everything works fine. If we don't have 16-bit normals, there's jitter in stuff because it just doesn't have as much data. And when we turn, you can see there's a jitter because 8 bits of data just isn't quite enough to do the fineness of it. But that option is there just to show you that. And if you really want to save some performance, it probably saves some performance to not use that extra 8 bits. So that's why that option was there. So let's look at the rest of this. But first, let's go over what we don't need to mess with that for. So the first thing we need to do if we're going to do our reflections is we need to get all of our data that we put in textures and unpack it. So our default color is the color at this pixel. For our normals, we're loading that color text to where we put it, and we're undoing that squishing. And then what we're going to do is we're going to normalize the X, Y, and Z components, just in case they got messed up. Our PBR data, we're loading that from color text 3, where we put it on each pixel. We take out our smoothness, which we put in the red channel, our reflective strength within the G channel, whether or not it's water was the B channel, and our F0 we put in the alpha channel. And then we're setting a value called far, and this is our adjusted far value, and we're just setting this to the render distance. If we were using this in horizons, this would be further, and this is setting the maximum distance that we're tracing our rays for the reflections, since we're doing this by distance, as I said, and not doing it with that screen space optimization, where it just stretches to the screen. Now, for our reflections, to save performance, we are only going to run them for certain things, and that's if the smoothness times reflective strength is greater than our reflection threshold, which was an option we could change, or if it's water. Because that way we're not running reflections on every single pixel on the screen as you normally would with some sort of like path tracing. But we're not trying to do that. We're trying to make sure this still runs good, but you optionally can do that. So this is our if, and if we trace this down, that encompasses pretty much all of the code. But before we go into that, let's look at some debug views we've got here. just to see our data that we've got. First, let's look at our PBR data that we saved. If we refresh, this is showing that PBR data. So this is both red and green, the iron, and the water is blue and red, and then gets more green as it goes away. So it gives us an idea of what's going on. So whatever green and red is, the iron is both. And the 0. So let's look, actually we may need to look back at our main function and see where we, I must have done something for that integrated PBR here. Let's see. So in our integrated PBR, we were already doing porosity and stuff for grass and for water. We added for iron and gold and redstone that its smoothness value is 1 and its F0 is 1. So that's going to destroy the PBR texture that we loaded as far as overriding it. But this gives us those values that we are seeing in our debug view. And it makes the iron work as a reflective surface, even without a texture pack. Let's go back in here and undo that. And let's look at our other debug view we've got here, which is our normals. And we take them and put them in a plus 0.5 times 0.5 just so that they're not negative numbers. Let's look at that. So these are screen space normals, so anything facing you should be bluish. Anything facing upwards is green, and to the right is red. And as you look at things, they change to be based on the orientation to you. So that looks like that's working pretty good. One of the other things that we use to visualize it, we need to turn off where our color is finalized here. And I believe I put it somewhere up here towards the top. Here's another little debug view just to see for us our position. And we'll get into that first because this is one of the first things we're doing is we're going to use it. So let's visualize this real quick because we need those normals and we need the position. Here's our position relative to the camera. So you can see it's like a grid. And as we turn, it turns with us because this is just showing where things are in relation to us so that we've got the data of where it is and what angle it's at. All right, so let's undo that. Let's make that visible again. And we should be just on our shader now that has reflections. So let's look at what we're doing here now. So in our first thing, our if statement, we were checking if something has reflections or not. And then here we're going to do the stuff to get them. So the first thing we do is we need to get the position of this pixel relative to the camera. So like as we did in the picture, we know where it is. So we take our text chord and our depth texture, do some stuff on them. And then we're going to save this position for our refiner later. So we know the first spot that this texture is starting at, the reflective ray, like where the pixel is. And then we're going to get rid of the perspective so that we've got just a 3D cubed space. This was something you could maybe play with, but there's some things in here with comments that are just options for you to see what things do and play with them. It's not a great idea, so we don't need to mess with it. What we do though is we're going to reflect the ray angle that's coming from the camera. Let's say that this is the floor off of that surface so we can see what's reflected. So we're going to say that our ray speed or ray direction is a normalized reflection of the direction something is in, which you can get the direction something is in pretty easily. So if this is our camera and we saw that we had that grid view, make this a little smaller, where we were looking, where everything was like a grid, that's saying where something is. So it was like this far to the left, right, and whatever, and it was showing us up by color. If we normalize that and make this just one long, then it turns that position into a direction. So if something is like, let's say, off at an angle like this, so it's 10 in this direction and 5 in this direction, if you normalize that, you just get the direction and you go, okay, it's in that direction. So by normalizing the relative position, we get the relative direction. So we reflect the direction of the pixel off of the normal, and that gives us the reflected angle, or the speed and direction of the ray. Our fresnel, which is when you look at things at a grazing angle, as we discussed in the PBR, they're more reflective. We take, this is just a way to do that, where we compare the normals of the surface and the ray. We apply our Fresnel exponent, and this here is just a way to kind of optimize it a little bit. And then the actual reflective power is going to be the F0 plus whatever is left over between that and 1 times the Fresnel. So F is then here our reflective, like how strong the reflection is. And then here we're saying something called ray position, and we're going to say that that equals this position that we've now got. So then we're keeping the position, the initial starting position, and we've got our current ray position. And then we've got some flags we're using. We're going to check if it's a hit. We start that as false, and we're going to check if it's out of bounds and start that as false because the pixel is on screen. Again, we are tracing out a distance. An alternative is you could do this in just with a screen, and that would probably be more optimized. And we're setting our tracing distance so that if the ray is going towards us, it goes how far there is between the pixel and the camera. It's going away from us, it's just going to go the full render distance. And then here's where we're going to do our ray tracing steps. So if we look at this, this is our first loop, and then afterwards we have another loop we do if there's a hit. And that's some other stuff going on there. So let's look at our actual ray tracing for reflections. So what we do is we have this optional where we have our screen space reflection steps. And what we're going to do is we're going to do this starting at 1 step into it until we go as many steps as we want. And we're going to keep going. So that's the and. Because again, this is where we start, is before this first semicolon. And then this is why we keep doing the loop. And then this is how we change the loop, is we're adding 1 to this increment of I. So I starts at 1. This loop will keep going until we get to SSR steps by adding 1 to I every time. So while we're under the amount of steps we want to take, we haven't hit, and we're not out of bounds, let's do this. And it'll keep looping it. So what we're going to do is we're going to ray trace with an exponentially accelerating ray. I'll draw a picture for this, just to explain it. Ray tracing just means you're going from one point to another, and you're tracing that ray. So here's our camera. Here's the water. Here's the pixel we're tracing. So we already got here. We knew that's the position it was. We made this into a direction by normalizing it. We reflected that normalized vector, and that gives us this. So we know which way we're going. We've got a trace distance that if this is the render distance, we're going that far. So we're going off that far. If we were to just, let's say we're doing 5 steps. There's 1, 2, 3, 4, 5. Let's pretend those are even. They're close enough. Then we'd be checking here, 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 and here. And that's not the most accurate, which is why we also do refinement later. By doing an exponential check, what we're doing instead is if we have from 0 to 1 here on a graph, like y equals x, it just goes like this. If we do it to the power of 2, it goes like this, where it starts really slowly and then starts going up really quickly. So if we trace this exponentially, it's something I like to do to keep the step count down, and it works good with distant horizons, is then it's going to check the first few steps really close, and then it starts checking further away as you get further away, which means you're more likely to get these fine details of hitting small things when you're up close and not missing something. Because if there's like a tree here, you might like miss it if you just check here and here, but if you checked here, you'd catch it. So by doing an exponential way, we're more likely to catch things that are close without having to do like a million steps. If that makes sense. I hope that makes sense. You don't have to use that. You could turn this to 1 and it won't do that. Doing it higher than 2 is probably not a good idea, because then it might do all of your checks in the first foot and then none for the rest of it. So what we need to do, is Okay, so our position is going to start at our starting position. It's going to add the direction we're going. And it's going to do that direction as far as we're tracing. So this right here would just equal the furthest this thing could trace, but we're only going to go as far proportionately as I over SSR steps. So if we look at that again, if this is our spot, this is our reflection vector, this is our distance, so the first part goes all the way here, and then we're going to say that depending on which step we're on, which is our I over SSR steps, which is that last part, that's what gives us its division. So if I equals 1, it would be here. If it equals 2, it would be at the second step, third step, fourth step, fifth step. And with our exponent, it's instead of doing them here, here, and here, it's doing those first ones close and that one up here. So it's saying that our steps are in this definite range. And that's how we get our current ray position based on which number of our loop we are out of the total number we're doing. So we've got that then in that cube space that we had on the right. So to put this back on the screen, which we wouldn't have to do if we were doing it the other way, we do our projection matrix to add get our W component. We divide by it. We do this stuff to get it back on whatever, and then this is our position of the pixel on screen. And this is just from the space conversion sheet where you would get this. And then what we need to do is we're going to check if this ray is off screen, which you could do a few different ways. You could do that, or you could just check if the clamped value is the same. But I think this explains it better. If the ray X value is off the screen at all, or it's like behind us, then like the ray is out of bounds. And if the ray is out of bounds, we're going to stop checking it. This is the sketchiest part of this tutorial, and it's something I don't like, is the way I'm doing a bias. When we're doing our ray tracing, I need to show some stuff. I've been just talking for too long. For purposes of debugging, we are going to go in here to our reflections and turn our Fresnel exponent to 1 so that we have just solid reflections everywhere. There's a problem with when we're ray tracing. Since we're reconstructing the depth of this water from the depth texture, it's not very accurate because it's squished the whole thing down with some sort of exponential thing. And when we reconstruct it, it's not perfect. So we have to add a bias so that when this bounces off, since this data might be kind of jagged, like it might be kind of pixelated like this from our view, instead of being perfectly accurate, we've got to account that there's errors here, or this might immediately hit and think it's under that water, and then we wouldn't get reflections going anywhere. So we've got to add some kind of a bias where we adjust the hits so it doesn't accidentally hit, because if this bias is off here, it might still hit on this next step. I'm going to show the depth texture in a debug view. We'll show how to do that, and we'll look at what not having a right bias would do so that you could see why it's necessary. First, let's show why it's necessary. We'll just do a bias of 0. And let's look at what happens to our reflections. And we can see that there's a certain distance at which they just don't work anymore. But they work good before that distance. And if I change the render distance, you can see that that changes. And I believe that that has to do with the way that we're linearizing the depth, and there's just an accuracy that's kind of lost there. I'm not 100% sure, so I do something kind of hacky to get get around this. I don't have this problem in my other shaders that don't reconstruct depth this way, but I do have it in this tutorial. So we're going to do something to kind of get around it. It's hacky, but it works, which is that we're going to add more bias. We're going to start with a bias of 0.1. We're going to add more bias based on how far away the pixel is. And then we're going to shrink that bias. Let's not shrink it first and just see what it looks like adding more bias based on distance. And then you can see now the reflections work all the way out into the distance. But there's like a distortion to them. You can see they look fine when you're down here, but as you kind of get up, see like they kind of aren't working right. Because that bias is adjusting where the hit value reads. Or instead of saying check here, it's saying, okay, it has to still be under by an extra amount to count as a hit to get around this. So if we shrink that as we get further from that initial reflective surface, it kind of limits that distortion. See, that kind of fixes it some. There's still some there. It's jank, and I don't like it, which is why I say you should learn what everything is doing from this and then make something better. That kind of adaptive bias based on the distance, it fixes us not getting reflections in the distance, and it adds some distortion that we can work around. Or once the water is wavy, you're never going to see it anyway, because like the waving water is going to be different. And as you can see here, like that reflection is more than good enough for our purposes. I wanted to at least get into this because this is a messy. I don't like this, but it works, so that's why it's here. So let's look at the depth texture real quick. Let's make another debug view down here. And let's just set our color to be our depth texture where we are sampling it. Let's go to the top here and look at depth text 0. And somewhere we sample it. We do so where we do it here, and we'll also do it later in our ray trace. Right here. Let's instead do take this vec 3, let's take this value, and let's do a fractional component of this depth texture, which we know is 0 to 1, but we want it to be visible, so let's do it times 100. And this should break it into 100 steps. Okay. So there's something. Let's break it down into fewer steps. Actually, it's giving us a 0 to 1 value instead of the depth texture. So let's this is our depth that we're getting once we run it through that function. So here's our depth into the screen, which isn't exponential at all. This is what we get when we're done. Let's look at what the actual depth texture itself was. Which is why that didn't read right. So that's our actual depth. Let's also look at just the depth texture. Let's label this. If you're using an IDE that checks you for errors, you won't have this problem. Okay, so again, as before, that's not visible. But if we wrap this in an exponent, it may be visible. There we go. So now if we do a really heavy exponent, you can start to see where this shows the distance, where white is far away and black is closer. As you see, even with an exponent of 11, you can barely tell. Let's blow this up to 100. Okay, so even at an exponent of 100, then it's almost looking linear. So you can see why there is some data loss there, where it's saving a lot of precision up close, but it loses precision as you get further away. But that's just how it saves the depth texture. But when we use our little function to get the distance, this is the data we get, and it just loses precision off on the distance, which I believe is why we were having that problem where we need an adaptive bias based on distance. So that's our depth texture, and that's what the data looks like. Here's what it looks like when we get it out. So let's go back in here at our code. Where were we? We've got our pixel position. We've got our ray tracing loop. And in this ray tracing loop, we were checking if it's out of bounds. If it is, we stop. We've got our bias. And then here's where we check our depth. We're saying that our D, which is our depth, we get the value at ray position.xy, which right now, because we've done this stuff, we've turned it into where it is on the screen, like a text chord, instead of being in that 3D space. It's not in the cube, it's in the screen space. So we get our depth, and we're saying that if our depth plus the bias is less than the ray position.z, and this ray position, as we may have seen, let's look here at it, at which direction this goes in, because it's either going towards us or away from us. It looks like it increases as it gets away from us. So we're saying that the ray is occluded if the depth plus the bias is less than the ray position, meaning the thing is closer than the ray. So if the ray has gone further than what we see, we're assuming that the ray has gone into it, but there's a chance it went behind it. So we'll account for that as well. So it's a hit if the ray is occluded or gone behind the thing, and it's not out of bounds. And here's where we allow it to continue if it went far enough behind something. We could turn this off to look at this and see what a difference would make, to see why that code is there. And you can adjust the amount. Let me turn off this debug view. So we're pretty much checking if it goes behind something. So you see here on this tree, you can't see behind it, like those rays are hitting it. Let me draw a picture for this, just in case. I want to make sure everybody gets it. You know, the whole point of this is to teach you. So here's the water, here's us, here's that tree. The depth texture just draws this as like it goes infinitely backwards. It doesn't know it's behind something. So when this ray hits the water here and reflects here, it just knows that it's behind the tree, so it's saying that's a hit. So if we say that it needs to not only be behind this, because here's where this pixel is here, but we're saying that if it's a certain distance behind it, just let it keep going, because that thing might not be solid, and that's a guess. So if this did go all the way back, we'd get a false sky read through here, but if we don't have it go all the way back, but if we do have it go all the way back without checking that if it's a certain distance behind, we should let it go, we get this problem with the trees, like this. So let's look at if we do let things go behind, by assuming things aren't infinitely deep. And this should fix the trees, but it'll give us other problems in other places. See there, you could see now here it allows this ray to go over behind it. You can see that other jank from our bias adjustments. Let's turn this back off and look at it again. Our refinement may be fixing that. Let me turn off the the refinement, because we didn't cover what that's doing yet. We may have a problem in our refinement, so we'll go over that. That is a surprisingly good reflection for no refinement. But see, we've got problems, which is related to the bias stuff. Conceptually, this is what this should be doing, is that it would allow it to go behind, so you'd see sky, and that this reflection of the tree wouldn't stretch for everything from all the water behind it. But it looks like my code is not necessarily doing it the best way. But that's the concept, and if you know the concept, you can see what's going on wrong and you can make it better for yourself, which is the point of this. The point of this is to good enough to teach you the concept, and I honestly don't want to spend more time on it. So that's how we're deciding if we have a hit, is if the ray has gone behind or into something, it's still on screen, and it's not so far behind that we're assuming that it went behind it. And then we're going to save our last ray position. If it's not a hit, it will be the current ray position. If it is a hit, it stays what it already was. This way we've got something to refine between with a refinement. So we've got the ray used to be here, now the ray's here. This was a hit, this wasn't. And we're going to refine between those two spots to find out where the actual hit was for better reflection. That's what this next step does. If we disable the steps, the refinement steps, in our options here by setting this to 0, it doesn't run any. And then we could look at just what these screen space reflection steps do. Let's look at this at the low quality first to see why these steps exist. So let's look at just 5 steps. And this is what 5 reflection steps look like coming off. And remember, this is going like really far in the distance. So you can see that there's like some misalignment where like things don't line up because that first step is so big that it just misses stuff. But if we pull these up higher, it's more likely to hit things, but we still have some misalignment just because the steps are going so far out that it adds this kind of distortion. But it's like, it's performance versus things. Like, do you really want to do 200 ray steps just to not have a little bit of distortion when the water is going to be wavy anyway, and it worked fine for a little piece of metal? And the answer is, in most cases, no, you don't. You want to have FPS. So we're going to do the low step count. Because even this 5 looked fine. So let's look at this, and let's look at what refinement steps do to it. So if we've got a reflection here, it already looks like it's pretty solid. If we weren't doing the exponential ray, let's see what that would look like, because it on its own already gives us just higher quality. If we do this at a 1, you see there it does that distorted squish even worse. If we were to do this higher, it would probably start to break down. And let's look at what our refinement does. Since it checks where the last hit that wasn't a hit and the hit that was a hit and goes between them, we can do that for however many steps we want to kind of fine tune. And you see what that does here, that without it, that distortion is really high. As we add refinement steps, it lines it back up and we get a better picture. We see there it's doing much better. Like that distortion is gone mostly, but there's still with that initial step, if it's missing, like it's missing the top of the tree, that's where we would have to add more steps to start. So if we did 10, see, then we're hitting the top of the tree, and maybe we don't need as much refinement now. And it's your screen space reflection steps and refinement steps that are doing texture reads. So those are what's going to cost you FPS. And if you wanted this pixel perfect, you would do like 1,000,000 steps and you'd be fine. But for most purposes, you just want it good enough. So you might even keep this at 5. And you see, that's what that looks like there. That's what it looks like there. So it's just a way to kind of balance the performance to whatever you want. But because of the way we're doing this, there's still going to be some amount of distortion, and some amount of it doesn't know if that's behind it or not. And that number there, you could, where we told it to check if something's behind it or not, if you change that number, it would change whether or not you get these false hits here, how likely they are to happen. But that's what the step count and refinement steps are for. Let's look at where the refinement steps are actually applied. If we do hit, we're going to run this code that actually, because now we finished our main ray tracing loop. If we were just looking for a hit to get our last ray position and our current ray position, so that we've got a range of where the pixel is on screen. So with our tree example, where's my cursor? When the ray was here to our camera, it wasn't a hit. When it was here, it was a hit. So we know that it's between this pixel and this pixel on screen, which on our screen here, if this is the tree and this is the water, we knew that this wasn't a hit and this was. So having those two positions, we are then going to refine between them, which means we're going to set this as the last position, this is the current, and just go back and forth and kind of fine tune. So let's look at the code for that. This is really common in reflection code and anything that's trying to get a hit somewhere. So we've got those values. So then if it's a hit or it's not out of bounds and the ray is going away from us, which means it's sky, we still want to read that. And this is the thing for that. We're going to refine our position. So we've again got our depth value. We're setting our position to the current ray position on screen. We're just reusing this variable. And we're setting our reverse value to -1. Our refined value is the current value that we've refined it to, and we're starting it at 1, meaning that between the last position and current position, it's all the way at the current position. And then we're setting our ray speed for refinement. And then we're going to say we're using a counter called RR, and we start it at 0 and go for how many steps we want and increment. And for each time we do this, we're going to half the speed, and we're going to add to the refined the ray speed times reverse, set our new ray position to be a mix between the last position and the final position, those two positions we had based on the refined value, check the depth at that position, and say that it's whether or not it's a hit is again if the depth is into it or not. And if it is a hit, reverse is 1, otherwise reverse is, or -1, otherwise it's 1. And what that does is that in our thing here, if we've got, here's a thing, and we know there's a hit, here's where the one position was, and here's where the other position was. If we draw a line, we see that the actual reflection should hit right here, but we read a reflection here. So the first thing we do is we go back by that ray speed that's half, and this wasn't a hit, so then the reverse value gets to be positive when we go half this way. That is a hit, so then we go half back out, that isn't a hit, so we go half of that distance back in, that is a hit, and we keep kind of doing this back and forth until we get the exact spot that we're at. That's what the refinement steps are. That's how I do it. There may be a more efficient way. That's how I made it up in my head. But I think it's very common. And by doing that, we have that refined position, this ray position here. So then after we've refined it, so there's some other stuff we do here to make things look better. We'll look at those in a second. But now that we've got that final position, that's where we then later will read our reflection value by loading our color text 0 where the actual information is at that new position. And we read out a certain texture LOD, which we'll get into that as well. So to see about fading reflections on the screen edges, let's get rid of this code for a second just to see why we have it. If we don't have it, you see that the reflection has a very strong cutoff where it just doesn't have data anymore, where something's off screen. That looks really ugly. So what we do is we apply a fade to the edge, and I'm doing that just based on this. I do one way for water, and if it's not water, I do it another way. And the result of that code is this right here. And you can look at that code if you'd like and break it down and do it differently if you want to. I just thought that having that fade the way I've got it is nice. You can make the fade stronger. You can make the fade less, but it's just to make it a little bit less abrupt. And when we have the Fresnel value for the water set to something more realistic, like even just a 3, that fade is kind of less obvious. There was set something even more realistic, a higher value here, it pretty much wouldn't be noticeable at all because that stuff looking straight up, it doesn't have a reflection anyway. So that's why this little bit is here. And then for doing rough reflections, we use our smoothness value to read at a different LOD, which is why on our color text 0 up here, we set it that we want to have mipmaps. What mipmaps are, if we haven't covered them before, is they are blurred versions of the picture. Where am I sampling this? And we'll showcase this real quick. So reflection, let's take this code right here, and let's just copy this into a debug view for down here. Let's say color RGB equals LED color text, and we'll set this at 0 to start because that's the default, and let's label this as a debug mipmap view. So this will get rid of reflections by overriding them with just what the texture value was before. This needs to be our text chord. So this is just our picture we had before, and to see what so we set that to 4, we're sampling the 4th LOD. The 11th LOD is just the average color of the whole screen. And we see the 6th LOD is very blurred. So we're using that as a free way to get a rough reflection, because if something is rough, it has a blurrier reflection. So we base our LOD by being 8 times 1 minus smoothness, meaning the rougher it is, the higher of an LOD will sample up to the 8th one. For 1080p and 4K, that seems to work okay. I think for 4K, 16 might be better, or 9 might be better. Each one doubles it. So an LOD of 1 samples 2 by 2 pixels, 3 would be 4 by 4, etc. So here's where we get our reflection by taking where our reflection ended up and sampling what's on screen. Here we apply a metal tint. If our F0, because remember from PBR episode, it also stores this thing as a metal. So if it's over that value, we multiply the reflection color by the albedo color of that spot to get kind of like a metal tint. We applied this to redstone and to gold as well, our IPBR, so let's check those. And if this is working, it should tint these metals. Doesn't really look like it's doing that, so let's see. It looks like I've got an adjustment here for how strong to tint the color. Maybe that's a bit more tinting. Okay, there we go. Well, I was doing that in the wrong direction for some reason. You can kind of adjust that for how strongly you want the reflections to be tinted. But in this case, you can see that if I set that to a higher value, it makes the reflection be tinted by the color of the thing to kind of just estimate very quickly and efficiently how a metal would do that. And if we put that to 1, it's going to change how that happens. And if we put that, if we didn't do this line, it would look like that, which isn't how metals work. So we've got that line there. And I think I liked that value of 2. So we're going to put that value of 2 there just for fun. Do whatever you want. You know, this is so you learn and do what you want with stuff. So what do we got next? Here's where we take that reflection value and we mix it into the screen. We don't just add it because when things are shiny, you don't see the scatter. You just see the reflection. So we mix it instead. So you kind of get only one or the other. That's if it's a hit. This was if we were doing reflections for that pixel. This is just our debug views. And here's where we write that final color to the screen. So that's all of the code. And isn't that kind of nice? We've got reflections both on our metals that in this case were defined. If we use a texture pack, it would use those texture values. We still have our IPBR overriding the values of the texture. So you could put a toggle to change that. And let's also look at the roughness. Let's go into our main file. And let's look where we were applying that integrated PBR. And let's say that if we wanted the smoothness to be 0 for the metals to be rough and not perfect reflections, let's see what that looks like just so we can check our code. So here we see we've got a very crisp reflection. Oh, it looks like we're under the reflection threshold now that we set. So let's turn this reflection threshold down. And so we want these to be half. And see that reflection is a little bit blurry, but not necessarily as blurry as we'd want it to be. There's even rougher material. You can see it's even more blurred reflection. But for testing purposes, we probably want that to 1. And most people would probably want that to 1. And in here, we may want to see how this check of if we're doing this pixel or not. We may want that to be greater than or equal to reflective threshold, so that reflective threshold of 0 would still work. So let's look at that and set the smoothness to 0. And then there we still got reflection, but it's very, very blurred. So that's a good little thing to add. And let's set this back to 1, because I'm going to upload this however we finish it. So that what you're going from is what you see. So let's reset the settings and make sure this all works. And it looks like we've got reflections. They're doing okay. They're fairly performative. I'm at 4K, so the performance isn't going to be the best. They work underwater as well. It looks like we can maybe make some adjustments to things, but overall that looks pretty good. We've got Fresnel. We've got we can read textures. We can do integrated PBR. We've got a little bit of fading on the edges of the screen, so it's not too bad looking. Everything's fade out. And we've got options where we can adjust the performance. We turn them on and off. This slider, I think, doesn't actually apply. It did in, I think, one of the files, but not in the other. So you might want to make that work or get rid of it. We've got our threshold for reflections to save performance. our Fresnel exponent, so we can change how that works. You may want to do that different just for water and for other things. Our steps, which I think we could get away with even just 5, we saw, but it's kind of a balancing act for performance. And then our high quality normals. So that's it. Let's look at the code again for a quick review. We'll look at Composite 4. The other stuff was just kind of accessories. So we're still using version 120. We load our settings. We load all our color textures, which includes all our already deferred data. We get some information we need for space transformations, where the pixel is on screen. We want to use mipmaps for rough reflections. This is how we turn our depth value into something linear so that we can compare it in a way that makes sense. This is how we move in and out of perspective. We load and unpack our data. We check if we're going to do reflections for this pixel based on always doing water and otherwise only doing things that meet our reflection threshold to save performance. We get the position of the pixel relative to the camera. We get the reflected angle. We calculate our Fresnel and how strong the reflection should be. We store that position for refinement later in case the first step is a hit. We set our flags. We set our trace distance because we're not doing it on the screen. And then this is our main ray tracing loop, where we go for so many steps until we hit or go out of bounds. And first we take the position, we exponentially accelerate it towards the ending direction. We get where that pixel is on screen by reapplying perspective. We check if it's out of bounds. We do a dynamic bias, which is very janky. And then we see if it's behind something. We check if it's so far behind that it might go behind it instead of hitting it. We update our last position based on whether or not this was a hit. We exit the loop if we've hit or gone out of bounds. And then if we have hit or we're not out of bounds and tracing towards the sky, we refine our position here. We fade our edges. We determine our LOD based on the smoothness. You can also apply the distance that the ray has traveled to this because it should scatter more as things get further away. We sample the reflection from our main color buffer. We apply our metal tint. And then we blend this reflection we read onto the screen. And that's literally it. That's the entirety of the code. So you've got this here to download and play around with. And I hope that those concepts make sense. I think the only thing that I did kind of janky is the way I'm dealing with that bias, which is there, unfortunately, only because of the reconstruction based on depth, I believe. I'm not 100% sure. I just know in that my other shaders that don't reconstruct depth, I don't have that problem. I don't know how many steps you'd want to run here. You could make this go even higher. You could do this to like 300 if you wanted, or whatever you wanted to do. But this, I think that these are good enough for quick reflections, and they will definitely be good enough once the water is all wavy, because it will kind of hide any imperfections going on. So what's next? You can also, if you wanted to catch cloud reflections that are off screen, you can say that if something is out of bounds, it should set to the sky color based on if the pixel's light map coordinate shows that it is exposed to the sky. You could also pre-render your clouds into a cube map, and then you can have the ray direction sample that cube map for rays that go off screen. You could do all kinds of stuff with that. But for basic screen space reflections, I think that that's about as much as we need to do to cover the concepts and have a working good enough version. And let's look at the performance impact. Let's reset this settings. Let's pump this up to maximum. And we'll compare them with not doing them. So at 4K, let's turn them off first. Let's see, reflections off. So with reflections off, I'm doing 490 FPS. What does this say? 500, because that's going above 500. And if we turn reflections on, we're doing 500 FPS. So it looks like a very minimal performance impact. And that's because we're keeping those steps down. If we pump up the steps, let's pump up these steps and the refinement steps. I still don't really see much of an impact, but you may on a lower end machine. But that's why those options are there. So that's it. That's this tutorial. Hope you had fun. The next one, we're going to get into different ways to do water surface so that we can have like little ripples or waves that change the way the reflection comes off. And hope you all had fun, and I'll talk to you soon.